All right, this is a homework debriefing on orbital mechanics, homework assignment 5, circular, elliptical, and Hoffman orbits. I'm really going to do this briefly because I've written a computer program on my graphing calculator that allows me to do stuff like this relatively quickly. So this won't be quite as detailed as perhaps you would like. Number one, a satellite orbits Tantalus 5 at a constant altitude of 758 kilometers above its surface. Tantalus 5 has a diameter, note that's not radius, of 27,500 kilometers and a mass of 5.55 times 10 to the 25th power kilograms. Calculate the orbital period of the satellite and express your final answer in units minutes. So what I'm interested in is realizing that I have a planet of radius capital R. I have an altitude above its surface of h, and the orbital radius will be the sum of the planetary radius plus the altitude above the surface of the planet. To find the period, the formula is Newton's version of Kepler's third law. T squared is equal to 4 pi squared r cubed divided by g divided by m, the mass of the central body, or the planet. So I would have to rearrange this equation to solve for r. R would be the cube root of gmt squared over 4 pi squared. So what I'm going to do is just take advantage of a program I've written, and that program is called Orbit. You can write a program that does this as well. You could work on your programming skills, it'd be great. So the central body is not the Earth, Moon, Mars, or the Sun. So I'm going to select Other, and it's asking me what is the mass of the central body, and I'm going to type in 5.55 times 10 to the 25th power. Then it's going to ask me what is the radius of this planet. Well, I have the diameter is 27,500 kilometers. So for radius, I'll type in 27,500 divided by 2, and that will convert it to radius for me. Boop. And so now I have the central body information for Tantalus 5. This is going to be a circular orbit, and I know the altitude of it. So I'm going to select circular orbit, and I'm going to select the option for altitude. And the altitude is going to be 758 kilometers. So here are the results. It says the orbit radius worked out to be 14,508 kilometers, which is an altitude of 758 kilometers. The period is 5,706 seconds, and to the nearest whole minute, that is 95 minutes. And that's a very high velocity, 15,976 meters per second. So this is substantially more massive than the Earth. And that's the result. I'm confident that I have the result. So I would say the period is 95 minutes. Now, if I want it to better than 2 sig figs, I have to actually exit the program and convert 5706 to minutes. So 5706 divided by 60 is 95.1 minutes. So I'll go ahead and record that to 3 sig figs as my answer to problem number 1. Number 2, a second spaceship also orbits Tantalus 5. Well, yikes. I don't know if I have that information still in my calculator. The second satellite is moving at an orbital speed of 3.14 kilometers per second in a circular orbit. Calculate its orbital radius. Well, it turns out my program, I never wrote it to deal with this sort of situation. So this one, I'm going to use the formula that says v squared is equal to gm divided by r, the orbit radius. And in this case, I want to solve for the orbit radius. So orbit radius r is going to be g times m divided by the orbital speed squared. And I got there, basically you swap positions in this situation. So if you want to do it in 2 steps, you multiply both sides by r, you divide both sides by v squared, and here's your result. R is equal to gm over v squared. So on my calculator, I will go and check what the value of the mass is by going alpha m. And it says, on my calculator, I use the variable called m as a storage for the value of the mass of the central body I'm working with. So I see it still has 5.55 times 10 to the 25th power stored in memory as m. And I always keep g as 6.672 times 10 to the negative 11th power. So I'm good to go. I go alpha g, alpha m, divided by, now to put in 3.14 kilometers per second, I have to enter it as meters per second. So 3140 squared will give me the velocity squared. And so, beep, 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 there is the answer in meters. Too many numbers to write down. I'm going to divide it by 1,000 to convert it from meters to kilometers. And sorry about how dirty the display is and corrupted on my calculator, but the answer is the orbital radius works out to be 376,000 kilometers to 3 sig figs, which is good enough for what I'm trying to do here. All right? So 3 sig figs, that's 376,000 kilometers. Problem 3. An Orion spacecraft, an Orion spaceship is in an elliptical orbit around the asteroid 6 Hebe. This asteroid has a mass of 1.27 times 10 to the 19th power kilograms and a diameter of 186 kilometers. And you can Google it and see I didn't make that one up. It's in our solar system. If the Orion spacecraft is at a periapsis altitude of 50.0 kilometers above the surface of 6 Hebe and an apoapsis altitude of 3 to 25 kilometers above the surface of 6 Hebe, then calculate part A, the semi-major axis of the Orion's orbit, part B, its period, part C, its periapsis velocity, part D, its apoapsis velocity. Well, I do have a program that would solve this one, but without a program, you would say semi-major axis. Okay, so I have this asteroid. We're going to assume it's circular, even though it really isn't in real life. Then I have an apoapsis altitude, and on the other side, a periapsis altitude. That the semi-major axis is equal to the diameter plus the periapsis plus the apoapsis all put together divided by 2, because semi-major axis is from center and it's average. Okay, so so that's one way to come up with the semi-major axis. To get the orbital period, let's see, what should I write here? So I should write 2 times the radius plus the periapsis altitude plus the apoapsis altitude, and then divide that by 2, and that'll give you the semi-major axis. For the orbital period, t squared equals 4 pi squared a, the semi-major axis, cubed over g divided by m. Part C, the periapsis velocity is equal to the average orbital speed, so I could calculate that using v equals the square root of gm divided by a, the semi-major axis. This average velocity times the square root of the apoapsis radius divided by the periapsis radius onto the radical sign will give you your periapsis velocity. And part D, the apoapsis velocity is the product of the average orbital velocity if you like, divided by this, or if you like, multiplied by the periapsis radius divided by the apoapsis radius. So I'm going to put all that into my calculator and just let it do the nitty-gritty details for me. Again, you could write a program that does this yourself, but make sure you debug it so that you have some confidence in it. I need to change the central body because it's not Tantalus 5, nor is it the Earth, the Moon, the Mars, the Sun, so it's other. The mass of asteroid 6 Hebe is 1.27 times 10 to the 19th power kilograms, and its radius is half the diameter. So if I type in 186 for the diameter, but divide that by 2 before I hit the enter key, then that'll enter it with the correct radius. Now this is going to be an elliptical orbit, so option 3. And what I can enter are the two radii for this orbit. And very cleverly, I've used the memory location called B to represent the radius of this central body in units of kilometers. So if I want to put in the radius, periapsis radius, and I only have the periapsis altitude of 50 kilometers on my calculator, I would go alpha B to put in the radius of the asteroid plus 50 kilometers. Boop. For apoapsis radius, again, alpha B to represent the radius of the planet. And this time, the altitude is 325 kilometers. Boop. So here are all the answers. The periapsis radius is 593 kilometers. And I see that it appears to be a periapsis altitude of 500 kilometers. So this stuff is all wrong because there's a missing decimal point on the second column. So I'm going to re-enter the elliptical information as 2 radii and try to be less careless. So alpha B plus 50. I thought I typed in 50.0, but it looks like it went in as 500. So I'll just leave off the decimal. No, I'll put in the decimal there. For apoapsis, B plus 325 kilometers. And now this looks reasonably correct. Periapsis radius of 143 kilometers, altitude of 50 kilometers. Semi-major axis of 281 kilometers, apoapsis radius of 418 kilometers, apoapsis altitude of 325 kilometers, a period of 32,066 seconds, a periapsis velocity of 94 meters per second, the average velocity was 55 meters per second, and the apoapsis velocity was 32 meters per second. There are all of the answers to problem 3. So what I'll do is I'll just copy and paste and say A was, the semi-major axis was 281 kilometers. The period was 32,066 seconds. More sig figs than I should keep, but I tend to do that. And I didn't bother converting it to minutes and hours on this particular page. Part C, the periapsis velocity was 94 meters per second. And part D, the apoapsis velocity was 32 meters per second. Okay, so there are the answers. Number 4. A Dragon spacecraft is in a circular orbit around 6 Hebe. Okay, so it's the same satellite as number 3, or asteroid, same asteroid as number 3. Its altitude is 45.0 kilometers above the mean surface of 6 Hebe, meaning average The crew decides to undergo a Hoffman transfer to a circular orbit with an altitude of 315 kilometers above the mean surface of 6 eV. Calculate the inner orbit velocity, outer orbit velocity, transfer orbit average velocity, transfer orbit periapsis velocity, transfer orbit apoapsis velocity. Delta V to depart the inner circular orbit and enter onto the transfer orbit. Delta V to exit the transfer orbit and enter onto the outer circular orbit. Total delta V for the transfer maneuver, and of course the time of flight for the transfer maneuver. In other words, do a complete Hoffman orbit transfer analysis. So I have this asteroid, which I'm going to model as a perfect circle, which it is not, an inner orbit of 45 kilometers, an outer orbit of 315 kilometers. Nothing I'm doing is to scale. I have to kind of in order, calculate the inner orbit velocity, then the outer orbit velocity, and then I build an elliptical orbit that just touches the inner orbit and just touches the outer orbit. Tangent here, tangent there. The semi-major axis will be the average of these two circular orbits, and that's how I get the semi-major axis. Then I do all the analysis as if it were problem 3 all over again. So I calculate the period for this elliptical orbit, periapsis and apoapsis velocities for this elliptical orbit. That gets me through C, D, and E. For F, I calculate the difference in speeds at this tangent point here between the inner orbit, which is going fast, and the periapsis of the transfer orbit, which is going even faster. So I have to speed up. That's delta V1. As I climb away from the Earth's gravity, I slow down so much that I'm going too slow to be in the slower orbit. So I have to speed up a second time, and that is part G. The delta V to go from the slow apoapsis point of the transfer orbit to the outer circular orbit. That's delta V2. Part H, add together these two delta V's. Part I, half of the orbital period of the elliptical orbit will be the time of flight to go from bottom to top. So I've written a program called Orbit, and I think I'm going to quit Orbit and just verify. So if I look at the body, it says the radius of 6 Hebe is 93 kilometers. If I check the mass, it says it's 1.27 times 10 to the 19th power kilograms. So I'm reasonably confident that I haven't changed the memory values in my program. So I'm going to launch my program and do a Hoffman transfer this time. Boop. What I have are the two radii. And once again, I use the variable b, it was my choice, to represent the radius of the central body. The periapsis altitude is b, the radius of the planet, plus 45.0 kilometers. The apoapsis radius is the radius of the body, b, plus 315 kilometers of altitude. And here's all the information we need to write down the answers on this assignment. So sorry, I guess you're not going to see me writing down the answers, copying the answers. For part A, the inner orbit velocity is 78 meters per second. Part B, the outer orbit velocity is 46 meters per second. And that is the only information on this screen that we're going to use, because it only talks about the inner orbit and the outer orbit, their periods, their altitudes. It's good practice to check and verify that the numbers that you put in are the numbers that are displayed. So yes, that's the right altitude. That's the right altitude. Life is good. I enter and go to the next page of information. It's all about the transfer orbit. So part C, the transfer orbit average velocity is 56 meters per second. Part D, the transfer orbit periapsis velocity is 96 meters per second. Part E, the transfer orbit apoapsis velocity is 32 meters per second. Part F, the delta V to depart the inner circular orbit and enter onto the periapsis of the transfer orbit is 17 meters per second. Now, I've chosen to round these values to the nearest whole number, nearest integer, I should say. And that's why things might not exactly always match, particularly when we're dealing with such small delta V's in the first place. Part G, the delta V to exit the transfer orbit and enter onto the outer circular orbit is 13 meters per second. And the delta V for the outer orbit to transfer orbit is always going to be less than the delta V between the inner orbit and the transfer orbit. Now let's keep my calculator on. No, I didn't really mean to do that. Let's quit. And sadly, I didn't copy the information over before the program ended. So I'm just going to run the program again because it's so easy to do, isn't it? B plus 45, B plus 315, and I should talk less and copy faster, right? Okay, so part H, the total delta V, the sum of delta V1 and delta V2. Here you can see 17 and 13 add up to 30, but the calculator kept it to greater number of significant figures. So it rounds it off to 31 meters per second. And finally, the time of flight would be half of the orbital period of the transfer orbit, and that is 15,394 seconds. Now, of course, I'm not going to give you the code from the program that I have chosen to write for myself. And you can create this code many different ways. For example, when I choose central body, I'm actually running a program called central body. And I've programmed into it the three bodies, well, four bodies of interest to me: the Earth, the Moon, Mars, and Sun as constants. Anything else, and you have to put in the parameters manually. So I like setting the central body to the Earth as a sub-program before I quit this program, so that I have the mass of the Earth and the radius of the Earth as kind of like the default pieces of information floating in my calculator memory if I need to just do a calculation that has the Earth involved with it. All right, what else to tell you about the program? You have to really carefully debug every possible error as you build it. I'm not going to debug your program for you, but you need to think long and hard about what happens if I have this situation or that situation. What happens if I put in the outer radius before I put in the inner radius? Will it even work? Or do you have to be careful and always make sure you put in the smaller radius first and the larger radius second? Well, what happens if you're going from outer to inner? That's going to be a negative delta V instead of a positive delta V for each one of the two delta Vs, leading to the strange but true statement. If you're going in a slower orbit and you want to end up going in a faster orbit, you have to slow down twice. Orbital mechanics. Isn't that nice? All right, good luck.